Hi everyone. Today I'll be presenting my work on neural machine translation for Sumerian English, which I carried out with CDLI during this summer. My mentors during the program were Dr. Nico Schenk, Ravneet Punia, and Dr. Jacob Dahl. So, a main objective in the project was to translate the entire Sumerian UR3 corpora with CDLI by making use of the specifically making use of the monolingual text across semi-supervised and unsupervised techniques for machine translation. So the primary motivation behind doing so was that we have about 1.5 million monolingual sentences, while only around 8,000 parallel sentences, uh, human human translated sentences in the CDLIS corpus. And the previous models which have been developed to for machine translation do not make use of this 1.5 million sentences, and even the parallel sentences that have been used are trained on the raw parallel text, and they are quite sparse and irregular, due to which the models are lack contextual understanding of the languages. So these are some partial phrases which are present in the raw parallel data. So you can see that there are about 2 to 5 words in both Sumerian and English in such cases, and if such sentences, if such partial phrases, as I would call it in my entire presentation, partial phrases or segments are used for machine translation, then the models are not expected to have contextual understanding or any references. So we reframe such sentences by concatenating the partial phrases to have complete sentences, which we can further train our models on. So firstly, we do this to have stronger baselines by doing a supervised learning approach on such complete sentences. We test across the various data configurations, and one such was the UR3 comp configuration, where we only use the in-domain UR3 corpora to train the model while using the complete sentences. So a complete Sumerian text goes into the N encoder blocks, which passes the encoding to the decoder, which gives one by one word by word outputs, which goes into the decoder again. And uh, in this manner, iteratively, we finally get the complete sentence. I won't be focusing much on the technical aspects or app or the model explanations, but more on how we solve the problems specifically to our domain, that is Sumerian English translation. So in this was one of the data configurations which we used. Another one was similar to what that has been used in the past, is the UR3 segment contain seg UR3 seg, which contains partial phrases and segments from the UR3 corpora. Again, only UR3 corpora, that is the in-domain data. So such partial phrases go into the model. So I show only one example here, but obviously there are around thousands of sentences which are used to train. So this is the UR3 seg, and then we have the all seg configuration where we use even the out of domain data from all genres of Sumerian text, but still the partial phrases. And then finally the all comp configuration, where we have the complete sentences across all genres of Sumerian text. So not only does this provide out of domain knowledge and out of domain language understanding to the models, but also complete sentences. And we found out that this type of data configurations gives us the best baseline, and we further use this to compare our semi-supervised and unsupervised approaches. Now, these approaches, we basically broadly divide them into three categories of self-supervision plus fine-tuning, data augmentation, and back translation. So now we'll see them one by one. Firstly, the self-supervision and fine-tuning. So self-supervision is a term that is used for machine for machine learning tasks which are done with or without references. But mostly what we do here is that we have some perturbations in the original text, in the original source of our data, that is the input, and we aim to have some output which could be derived from the input itself. Like for example, we used the masked language modeling, that is MLM, and translation language modeling, that is the TLM tasks here. So in the masked language modeling, we mask one of the tokens from our input sentence, and the aim in this, the task here is to predict this masked word. So as you can see, we only have an encoder here. So in the self-supervision phase, the self-supervision is used for the pre-training of the model. So we use the encoder to pre-train our model, by to pre-train the encoder basically, by using such self-supervision techniques. So tasks, I mean. So this masked token is to be predicted, and we pass the sentence as we were doing before, but now the encoding directly goes to a feed-forward layer and a softmax layer, and the output is obtained here. Like the masked word originally should have been this, and that's what we need to predict. So performing this and the translation language modeling, where we do not only have one language in the input, but we have Sumerian as well as English both present together. So we have a partial phrase, or one part of the sentence is taken from Sumerian, while the another part is taken from English. So we do this and we pre-train again using the self-supervision task of TLM, and now the Sumerian and English tokens have been masked again, and the objective is same. So we see that using TLM gives a huge rise in the performance also. So in the pre-training phase, we perform these MLM and TLM tasks to have a pre-trained encoder which we further fine-tune using our original model, that is the stacked encoders and the stacked decoder model. So specifically here we experimented across XLM and mass, which is another configuration of transformer. So for fine tuning, we again have two approaches, either of which could be used. So in the denoising autoencoding, our approach is similar to what we just saw in masked language modeling, where some perturbation is applied across the input sentence, and our task is to predict that output the same input sentence again. So this is done for fine tuning, and as you can see that no parallel sentence English sentence is required for such a task. Thus it is an unsupervised technique, the denoising autoencoding, while the another approach is machine translation, which we all know is uses a reference target sentence in English to train the entire model. So that would be a semi-supervised approach, because we first used monolingual data to pre-train the models, and now we are fine-tuning it using the parallel sentences. Thus we have the either of these could be used, and we experimented across both of them. Yes, so further, one major problem that we faced during these processes was the problem which we would like to call the catastrophic scarcity problem in Sumerian and English. So this problem is that the target level sentences that we have for in our parallel data, which have been human translated from Sumerian, are basically translated on a small words of partial phrases or very small phrases level, and thus the English side English side text or in a corpora is very distinct and very different from what the modern day English corpora would look like, because as we know that uh, translating a Sumerian, translating a source sentence word by word would be very different from, because the subject word agreement is completely different in Sumerian as it is to English. Thus, the parallel corpora in our case is very incoherent with the general English text as is seen in general datasets. Thus, using those datasets to perform the monolingual tasks like MLM and TLM for English or target side sentences is very is actually affecting our models negatively, because they do not actually understand the language which we require, which is actually in our parallel data. So we do data augmentation in this case because we have very limited target level corpora now, which we did not actually expect in the beginning of the project, because it is known that there are a lot of sentences and corpora for English, but in our case it's very limited because of the catastrophic scarcity problem. So we do data augmentation by using three techniques of BERT, WordNet, and CarSwap. In BERT, we basically, in all these three, our main objective is to do some word or character level perturbations in the input while retaining the actual meaning, but still having distinct sentences. So we do this over the target side English sentences to obtain our uh, augmented text, which if we use one of the three techniques, we get around three times our target site corpora. If we use two of these approaches, we get about, I think there's a mistake here, an overlap, I think. So we get about seven times our target site monolingual corpora, while if we use all the three approaches of BERT, WordNet, and CarSwap, we get 12 times that size. So we use this resultant target side the different combinations to perform the monolingual text pre-training and the fine-tuning phases, and we note the differences, which I will present later. In back translation, what we do is that we make use of the source side monolingual text in a unique way, that first a normal supervised technique model is trained as we showed, as was shown before. Then we divide the source side monolingual data into n we divide it into n parts or shards, as we call it. Now the one of those shards is translated to the target language using the model which you trained in step 1. Then those shards are concatenated with the parallel corpus, that is the first shard, which is the adjacent one, and the resultant which we obtain from it are concatenated, and the model is retrained on that. So this is done over all the n shards, that were 8 shards in our case, of about 80,000 sentences, monolingual sentences each. This is how we perform the back translation technique. So we in the last step, so we basically have the entire monolingual and parallel sentences together, and also the target side sentences, and the entire model is retrained to obtain the final model. So the experimental results I show here across the different techniques I just explained. So the supervised approaches across the 4 configurations which I showed is as follows. So the all comp configuration outperforms the UART3 seg. That was the most basic configuration by more than around 8 or 7 blue score. And while the UR3 comp is also while the UR3 comp performs even lesser than UR3 seg for some reason, and it's around 3 blue score of difference. And we show that the back translation, 5 times back translation, that is 5 shards of back translation, uh, show the best performance on vanilla transformers. And we get around 44 blue score with that, which is quite high. For the last year, the best performance was by LSTM, that was 20 blue score. So we effectively outperformed the last year models by 25 blue score. So in the self supervision, that is the XLM, which I just explained before, we get these scores, and these are significantly lower than the supervised and self-supervised techniques. But there are certain other reasons for that. That is the XLM uh, and MLM TLM approaches used only 4 encoder and decoder blocks, while for vanilla transformer we used 6 of them. And so this was because of certain limitations in compute. And but what's interesting to note here is that when we use the TLM approach, uh, on the original data set, that is with data augmentation, we get about 30 blue score, while when using all 3 configurations, while if we are not using any data augmentation, we get about 25. So there's a significant improvement as can be seen from data augmentation, and it was a very unique approach which we used for that. And this graph shows the variation in the blue score as we add more shards for back translation. So the highest performance, as was shown before, that was with 5 shards, and it was for around 44 45 back blue score. And we also show that using data augmentation, that is shown by the yellow line here, we also have a regularizing effect. That is, the loss curve decreases significantly faster and smoother as compared to the other approaches. So we also perform interpretability and interpretation techniques for our models which we train for machine translation, in order to obtain how the models are uh, actually understanding the Sumerian and English texts. So we have used gradient based and perturbation based algorithms, and we obtain net attributions for each output token with respect to the input tokens. So here, firstly, we have the human expert visualizations that we asked one of our human expert in Sumerian to uh, make these highlights for us, that what word we expect the model, or what the model should actually be looking at to give this output. So this is the actual output, and these are the human visualizations. That is, for example, for rations, it should be looking at this particular span of Sumerian text, and we see this, note this for our models also. So our interpretability code and program basically does this highlights for us. So we see that when using data augmentation along with XLM, the we get much better highlights generally, but not always. So in cases when so one of our methods to evaluate how good a model is referring to the context is comparing the some obviously comparing the human expert visualizations, but also to see certain words, like for a word like off, it there is no direct Sumerian uh, direct translation from Sumerian to off. Thus the model is more expected to look over a larger context for that, rather than just focusing on one particular word. And we see that the models actually do that. And while for words like barley, which are present uh, a lot of times in our corpora, the models are expected to focus on one particular word as shown in human expert visualizations as well. So this is shown, like, for example, in this unsupervised technique with TLM and XLM, the model is referring to a higher context, while for a semi-supervised approach with data augmentation, which also had a higher blue score of 30, we see that the model is more attributed towards one particular token that was desired. So we perform these uh, attribution techniques and we evaluate our models using this also, and we present a more thorough analysis in our paper. So one potential usage of this interpretability and even the machine translation models in general is for the expert human experts to decipher the meaning of phrases and Sumerian text which do not have a clearly defined meaning yet. So we can use such visualizations to obtain which for which Sumerian text, English which English tokens are the most relevant ones to look at, and we can obtain an estimate the of the English translations for a technique for a sentence. So the future work that we aim to do here is that we need to solve the issue of the UTF encoding in our Sumerian text. That is, certain words and discriminators which we need to have in the Sumerian text uh, are not currently present because of some Python encoding issues. We need to solve that, and we also need to dissect. We also plan to dissect the problem of catastrophic scarcity for more languages other than Sumerian. Further, we are planning to deploy the Sumerian English translation pipeline to the CADLI framework so that anyone can use it to translate the Sumerian text to English. And further, we also wish to work on the interpretability algorithms and on their potential applications. So that's all from the presentation. I would like to show special gratitude to Emily, Jacob, who supported me throughout the program and helped me with evaluations, and starting from the first data processing step to the last human evaluation steps, and also to Ilya and Lafont Bertrand to for their human evaluations, and specifically to the entire MyDark team. So my future plans after this project is to continue tuning and improving the project throughout the coming year. Then I'll be happy to invite and guide future contributions to the project. I would also be very interested to work on more developments around NLP for CDLI and cuneiform languages, and I'll be happy to do that as a Google Summer of Code student for the 2021 session. So that's all from the presentation. Thanks a lot.